Thank you. So what we're going to do now is we're going to derive a so-called linear quadratic regulator. Full-state feedback controller, which means that for a system with the dynamics described as follows, we will set the control to be proportional to the state. So for each state from the state space, we can easily get the control vector by just multiplying it from the left side by a gain matrix K of proper shape. And it will be optimal in the terms of the following cost function. It's the same as we did previously, but just for the continuous case. And for the Q and R weight matrices, we require the same properties to hold. This one matrix is positive semi-definite. This matrix is positive definite. And here we're going to suppose that our initial position is some state x naught, excuse me, some state x naught. What we're going to do next is we're going to try to reformulate this cost so that it will become evident and obvious about how to control the system. And please ask me about each and every step if something will be not clear. Please stop at any point. So let's do the following. Let us add and subtract before the integral the following thing. And P will be the matrix that we don't know yet, but there's just such a matrix. It will be symmetrical, but we don't know the value. So we have added and instantly subtracted the same thing so that the value of the total cost, the number didn't change. Next, let us move this negative apart under the integral.
Is it clear how did we do this?
I just want to ask what we are trying to achieve.
We have first formulated this cost, quadratic cost, and now we're trying to find this gain matrix for us then to be able to instantly get the proper feedback if we are in a certain state. This is called full state feedback. And we'll be keeping reformulating this cost so that in the end it will be divided into two parts. The first is the first will contain the initial conditions basically, and the second will be 0, and it will be obvious how would we make it be equal to 0. So we are going to make this cost as small as possible, and in the end it will be evident how to minimize it. Isn't clear how did we move this part inside of the integral? Yes, it is, right? Okay. Now let us use the product rule.
Should we keep the negative? The sign, the negative?
No, because what if we integrate this thing? It will give us x transpose b x from 0 to infinity, and at infinity we assume the system to be stabilized, so x is 0.
Okay.
And here at 0, it is x naught, exactly with the minus sign. So please keep asking me these questions if something is not clear. Just ask me. Okay, let's now use the product rule to the first term under the integral. Right, we have just the derivatives on the left and on the right. And now let us use the equation of the dynamics of the system. Let us substitute x dot with just this expression on the right.
Sorry to be so explicit, but like, could you write out the product rule for like matrix? So because matrix multiplication is an associative, does the product rule, like when we do the product rule for the differentiation, does it make?
So here B is a constant matrix.
Yeah.
So that's why we have just two terms. This corresponds to
So we're taking the product rule, it's always the derivative of the first function first vector here in this case times the bx. Okay, so
Yeah, so
okay, and yeah. The associativity matters, right? Like, yeah.
but we're not changing the order.
Yeah.
Okay. It's fine. Let's just expand this. Now we can group certain things here. So the first thing we are going to do is we are going to complete the square for u.
So when we're transposing ax plus bu over transpose, can you expand that out?
Yes, yes, sure.
Okay. This is like a property of transposing.
Yes, yes, exactly. Okay. So when you're transposing product of the matrices, they are being transposed and in reverse order. Okay. So we would like to see something in the form of Q plus some matrix M transpose R U plus the same matrix M minus matrix L. This is the form that we're looking for. So we have a full square over here. U transpose RU. This will correspond to these two vectors multiplied with the help of the R matrix. And there will be something else in the square, and it will contain X in itself because we have these cross terms here.
Could you say that again?
Yeah, we're going to complete the squares.
Okay. Complete the squares. But okay.
So you know that completing the squares.
Yeah.
Yeah, so we're doing the same, but for the matrices. And this is the form which we're looking for. So we're going to express certain elements of this expression in terms of square, full
We
square.
immediately see how that translates to completing the square. Like if we have
No, we don't immediately see. That's why I have introduced a novel matrix M that we don't know yet, but we'll have to find out. M and L. We'll have to find them out. Those are for convenience. So they mark for us something that we don't know yet.
okay.
But we'll expand this and try to equate certain things to the things that we already have in our expression.
Okay. Okay.
It's a method of unknown coefficients.
Okay. When we do regular completing the square, like we have an equation in terms of, let's say,
Yeah, let's consider an example.
yeah,
Okay, x squared plus 4x plus 17, for example. And we're looking for something like this.
yeah. So half of the coefficient of x. Yeah. And to do so, we would take like half of 4 plus or minus, like half the coefficient of x, 4 divided by 2. We add and subtract, and then. So what is equivalent here?
Let me expand this, so it will be pretty clear. We get U transpose R U. The second term that we're going to have is M transpose R U. The cool thing is that this is a scalar, right? It has the same matrix M. Well, it's a matrix, I'm calling it a matrix, but it's a vector of the same size as U, because otherwise we will not be able to add that. So this M is a vector, and M transpose RU is a scalar. So the scalar transpose is the same scalar. So the second term, the third term, which is U transpose RM, is actually the same one. So we can just write 2 here. Okay, I can expand it. So let's see. The third term is U transpose RM, but if we transpose U transpose RM as a scalar, it's a scalar. It will be-
You showed me. Yeah.
Okay.
Okay. Yeah.
And the R, we assume R to be symmetric.
Yeah.
Okay, so we basically have two of these guys here, and the next one is M transpose RM, and the last one is just minus L. So we're going to try to find the correspondence between these elements over here and the elements of the original equation. This corresponds to the last term over here. That is present here. Okay, what do we see next? Next is 2M transpose RU. So U is in the end. And yeah, actually we can do the same as we did here with this 2 over here, because this is a scalar and this is the same scalar.
Right.
Yeah. So I can write it down here for convenience. Should I? Okay. So it's the same as x naught transpose b x naught plus an integral By the way, I can move the x transpose and x from both sides. I mean, I can reformulate this in the following way. X transpose here, A transpose B plus BA here plus Q. Do we just the shorter form of the same thing? So this thing corresponds to these three. Okay?
Yeah. Okay.
And the remaining part is 2x transpose B U. These two, and yes, that's it. That's it. Nice. So let's. Oh no, I forgot this one. Let's view transpose are here. And this thing from the expansion corresponds to the very last element under the integral, and this thing over here is going to correspond to this thing over here. You see, because it has U in the end. So what this means is that 2M transpose R U is going to be equal to 2X transpose B U. We are working to find an unknown vector M at this point. So we're trying to find it. And
Yeah.
it's going to hold for all the vectors U, right? So we can
D
virtually remove it. We can remove the doubles here. And what this will give us is that M transpose is equal to X transpose B R inverse.
Yeah. Okay. Yeah.
Or we'll need it at some point. Just M without the transpose is R inverse. For the symmetric matrices, the inverse is symmetric as well. B transpose is not symmetric, not necessarily symmetric. Usually not symmetric. B, which is symmetric, and X transpose, which is just X. And we are almost there. So let's plug M over here and see what happens. Let's expand this once again and find L. Okay, we can actually plug it here, right? So these things I'm going to write them here, plugging M into them. And it will be U transpose R U plus 2M transpose, which is over there. X transpose B R inverse, then RU. And
Could you repeat that part again?
Yeah. So I have
Back to
plugged
we're trying to find L,
transpose
right?
here.
We're trying to find L now. We found M and
Yes.
S transpose.
Yes.
Right. How do we find L? Can you start?
We are going to plug M here, and there will be some, so to say, extra part, some residual,
Okay.
which will allow us to find L. So it's like the extra 4 that you get out of expanding the square here. It's the same thing, just for matrices.
Okay.
Okay, so I have plugged M transpose here, and this gives us this expression. And the last part is the following. It's just M transpose RM. So M transpose, yeah, X transpose, B R inverse, R inverse, B transpose, B X. I can go faster or slower if needed.
Just a second.
Mhm.
Just figure out.
Is R transpose D the same as R?
Yes, yes, it's symmetric.
How did you complete this course? Where did you get
I did not complete that exactly. I'm in the process. So we're just direct. So what I did is that starting from this part, I'm trying to complete the square. So we assume a part of that expression to have this form, and we have two unknowns here. The first is M, the second is L, and I'm trying to represent what do we have here in terms of these matrices. So I'm going to find them. Here, I have equated well, we have to see the correspondences. This part is literally just this part, and that's it. It's the same. And now I'm equating the second term from the expansion to this term over here, because both of them have u in it. And this gives us that this thing has to be equal to this thing. And that gives us an opportunity to express M in terms of the rest of what we have. Okay, so M is like this. And now we're going to find L. And I'm plugging the value of the expression for M in the expression for, well, in this expression, basically, expanded. Yes. Yes.
The first thing, in completing square, we found the UTRUs and the two MTRUs. We found it, right?
Yeah, so this just corresponds to the last term over here.
And we found this to be that.
Yes, yes.
So can we equate the MTRN minus N to the X transpose bracket A T plus?
Can you show?
We found this to be that, and we equated this to this. So right now, this equals this, right? So the only thing remaining over here is this, right? So if we think since we found
yes,
this,
yes,
the only thing remaining is this.
Okay.
So if we substitute M over here, and rearrange for N, we can just find L like that.
I think so.
That's what that.
So, do you want to continue? No, why? You can, if you want.
No, I'll try and look.
Okay.
Keep it.
So, what L would you? fine. We can cross R, right?
Like we have MT and we have R and we have the whole X areas. So L would be M transpose
Uh-huh.
M transpose R and minus X.
Minus X, you mean minus this?
Yeah, this whole.
No, let's keep it. Let's leave it like this.
Oh,
I mean, we're trying to complete this square here, and we will get something in terms of X. Do you follow? Or okay. So please complete your thoughts. So what did you want to add here? What else?
no. I was just thinking because we finished the UTRU plus 2 MTRU part.
Yes.
And
Yes, sure. Okay, yes.
okay, wait, once you expand this,
Yes, uh-huh. So, do you think that there should be
this
something
is the
else?
remaining. Once you expand it,
Now, this is M transpose RM minus L. Okay. So we have just plugged the expression for M in here. Right. I agree, you're right. So let's finish this. And so under the integral, we have this part, we have this part, both of them are here already, and the rest that we have is this, which has to be equal to 0, right? In total. So L is equal to X transpose B R inverse B transpose B X, right? Who agrees? Who doesn't?
Q, we're missing Q.
Hmm?
We're missing Q.
Q, where?
Like we have Q in the main equation, but there's no Q in
Okay, so why is that a problem? No, not really. It's fine, it's fine. But the thing is that we have X on both sides here. And we're going to move this into the first part of the expression under the integral.
I lost you.
Ah, okay. Okay, so what I'm saying is that this thing, this integral, is equal to the thing that I'm going to write now. This is just the part
Okay,
with you.
Okay, yeah.
And the last part, the cool thing is that here we have x transpose and x on both sides. So you can move this middle section over here.
Yeah.
And we'll get two parts. The first is the weird square of x with
okay.
some combination of matrices in between. And the second part is this thing over here.
Okay.
And now that we remove everything from the left part because there's no space left, we will continue. It's supposed to be, yes.
Yeah, the left side is good. I think the right side is also not too bad.
Me too. So, you will.
Send you that closer.
You feel a part of this index.
Okay, so the last step that we have to take is okay, I'll remove this because the last step could require some space.
The same thing makes sense. The same thing makes sense.
Yeah, I agree with you, mate. I appreciate it. I need to expand it out myself. I need time for that. Work it through.
Because we're trying to complete the squares for the very last part under the integral, and there's no terms here that do not have a u in them. So, as it was correctly said, we are completing the squares for something like x squared plus 9x, and that's it. So it's basically the same as for matrices. It will be x plus 3 squared but minus 9. And this minus 9 is our L. Okay, so let us write it down. It's not transpose the x naught plus the integral from 0 to infinity of x transpose a transpose transpose P, I believe, right? Plus PA plus Q, plus Q minus that boring long thing. B or inverse. B transpose P. And its X is here. Plus plus this square.
So now,
Okay.
so now there's no end.
Yeah.
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 Because it's the
Okay, this makes sense.
Yeah, it's not makes sense.
It's starting to make sense, yeah. You're seeing this.
Yeah, that's why.
Yeah.
XT. I'm not zero. Because I thought it's a whole thing.
Okay, other questions regarding this? Or we're headed? Yeah. Awesome. So let us observe what do we have here. We have added and subtracted this expression with P. So the resultant value of the cost is not dependent on P anyhow. And if we change P, we'll not change the total cost.
Yes.
And now let's take a look at what's going on here. This is a square of this vector, and this matrix R is assumed to be positive definite strictly, which means that this term over here is positive for all the vectors, these vectors, if they are non-zero. However, we can equate this term to zero if we set this thing to be precisely zero. So the second term under the integral would be zero if so our control satisfies the following expression.
Just a second. So like, it won't be zero. Wait, so okay, R is positive definite, right?
Positives R is strictly positive.
Strictly positive,
Definite.
So definite. So if you want that term to be zero,
The only way to do so is to equate this vector.
okay, why do we want that term to be zero?
Because it could not be smaller than zero.
Yeah,
Because
yeah,
this is
of
the
course.
same vector, and this matrix is strictly positive definite.
Of course.
To minimize it.
Like we want to minimize the cost, right? So
Yes, since we want to minimize the cost, so we cannot minimize this really directly. Anyhow, the value of the cost is not dependent on the matrix.
right, it's not made directly. Okay.
Yes, but we have added and subtracted. So we can set it to be, I don't know, 100, 100, 200, that's no difference in the resultant cost. So in order to minimize the total cost, we want to minimize the integral. In order to minimize the integral, we'll try to minimize this integral at each instant in time. And in order to minimize this, we actually have to set it to be equal to zero. It could not be less than zero.
Okay.
That's why we're going to require this expression to hold.
Okay. Now we consider the next expression.
Yes. After that, we're going to consider this.
You know, right here, both of this that's there. The U plus R minus 1 expression is occurring twice for
where?
R.
Where?
Here in the bottom. Like it's twice, right? They're both the same. So can we not write 2?
It's here's the matrix multiplication. So I was just lazy to rewrite the same thing again. I can do it, but it's the same but not transposed.
Okay, I'm beginning to see what this is going. We're going to set K is equal to R inverse BT B. Right. Now, how do we get that?
Here we see another square, but the difference is that here we cannot equate x to 0 because x is the state.
No, we can't say X is the state. We can't say
X is the state, right? But what we can do is we can equate this whole thing to 0.
You mean how does
Why?
We will require this to happen, and we can find the proper value of matrix P that will nullify everything that is going on in
The
between.
one in the bracket is similar to R,
Well, in a sense,
because X is the square.
yes. So we're trying to zero two squares. One of them is this one. One is this one. But here we don't have any influence on R, so we can influence on the vector. And this is the other way around. We cannot influence X, it's the state. But we can set this to be equal to 0, and it will give us A transpose B plus BA plus Q minus B R inverse B transpose B equal to 0, which is a matrix algebraic Riccati equation that could be solved numerically.
So, the minimum cost will always be X naught T B X.
Yes, and it's the profound result because the cost depends only on the initial state, nothing else.
Huh.
Wait, can you repeat that?
The cost of the stabilization will depend only on the initial state, and nothing else. And the rest will be equal to 0.
Huh. So if you find P using whatever that
Yes.
is called.
Oh,
If you find
okay,
P.
so that would be the P and you don't have to solve the other J.
Yes, we would have to find.
Oh,
If you find P, then we can find.
Because that would be the initial state times P times its transpose.
Yeah. Yeah. I think. Yeah. I think. Yeah.
So then how do you create?
K is equal to the minus
R
I.
R inverse P.
Yes, so this is the control, and it includes matrix P that we have to get out of the algebraic equation.
No, we need to know what the algebraic equation is.
Not really. Well, we'll consider an example. But it's just the quadratic matrix equation that is being that is difficult to solve by hand and paper. That's what we need to know. So it is usually boiled down to some kind of quadratic programming thing, some kind of iterative process with an intent to minimize the error. And if it's small enough, then we're close enough to the solution. There is no exact solution, of course. Even for systems like a cart on a pole, analytically solving this algebraic equation is equivalent to solving a polynomial, finding the roots of a polynomial, or not a polynomial. Well, there are 6 unknowns there. 6. It's a big system, and it's non-linear, so it's very tedious. I'm not sure that it's possible to do it by pen and paper for for reasonably small systems. Yes, we can use solvers in Python. Yes, we can use numerical methods. We're not going to solve this by hand. We're just, well, we actually will, but just one time. We'll take a look. And for a very small system, right? So, what's coming? We don't have much time. So, are there any questions so far? Remaining questions? Or you need some time for this to sink in? What is it? Okay, let's spend 5 minutes sinking in.
What do you ask?
I'm going to expand and figure it out. Okay, so what I answer? That's actually so that's the motion.
If ours is on the right, yours is probably down
because
square on.
this thing is a scalar.
That's
matrix, which is those three, you'll just see a big board. You will see a board.
Yes, this whole thing, this whole result of multiplication is a scalar. And it transposes scalar. No problem. Because of the shapes. So let's take a look. X has the shapes of so it's a cold vector. B has the shapes of n times m. So
This one is
this is a square matrix n by n. This is not necessarily quadratic matrix, it's a rectangular matrix, but we type so say of the vector is n.
That's what
And it has to be multipliable by the normal matrix. And in the end, to get the vector,
It's 3
we
divided by 35%.
to the vector of the matrix. So
If you did one,
that's why
you'll get like 85%.
basic matrices with
Yeah.
so we take a
No,
look
but like,
at what we want with this multiplication. We get the following.
Light was
It's,
average until the last. So it was
Yeah.
100,
1 by n
85,
times b transpose,
25.
which is
The last one, but it was 1%. But the last one,
here we have p, that is n by n, this we replace
the last one,
and
no, it's harder if you
so
study.
multiply it, we
You
get
just lose the one who studied at the end of the course.
here, then we multiply it,
Like by the end, the last quiz, I never
and
did
it results in the vector m by 1, then we multiply two such vectors, and again it's
No, but I knew that one quiz was wrong, so I literally did not study. I focused on others. Because my quiz was average.
it's
But it's very fun. It's fun. This is fun. It's like a big fun. The best way to learn it is go on Expo Day. When you reach chapter 14, the next one. Go on Expo Day and draw it.
let's just
As a senior, I have a senior, I have a long time.
no problem.
Draw them. I should draw them.
I took it longer. Okay, so here transpose b
Barbie and
transpose
Barbie.
b x. Let's transpose all of this.
I feel like Barbie camera.
It will be x
Brother's giving Barbie.
because b is equal
Yeah, that kid's giving Barbie.
to transpose transpose.
You can Barbie like in like after
And
lunch.
it's they are both scalars. And it's a nice trick. You can transpose scalars for convenience. If you are too lazy to carry two in the same values.
I think it looks better without it.
Thank you for the question.
Everyone should stand for me.
Let's have her party.
No, everyone needs to This is not your card, so I feel like just exercise. We're gonna find out. You want to come this? Okay. You can tell me how it works. This is my main trick.
I know how it goes.
I don't know how it works. I'm sure that they come to Next Friday. I feel like
Oh, yeah.
This is my second reason. See that we can choose like any 9 carbon or 10. So we have 3 10s. We have a second. So we have 3 10s. Remaining cards in my hand. 1 card from this deck. 1 10. 1 card from this deck. And 1 10. 1 card from this deck. And 1 10. So now the 10s are like all arranged and mixed up in here, right? But we're going to imagine those 10s coming up to the top. The 3 10s will be placed. That's in between will come to the top. And 1. Others are in process. It's I don't remember. Tell me when to stop.
Yes. My favorite one is the tea one. Yeah. That's when you ask her to shuffle this much over. Yeah. I tried to. This is a new cut. On the day she shouldn't find them. You need to be have you seen Now You See Me? The girls who go
I'm learning a new one. I was going to
learn
learn
how
how
Now You See Me one. Now You See Me. Yeah, let's feel awesome.
Okay, so tell me when to start. Okay, let's start. Let's continue the erasing process, right? Help me out. Someone. It's such a pleasure to write on this whiteboard. Yes.
Oh, erasing. No, I don't think I don't know. Okay. There's a teacher's special. Correct. I like your teacher. No, those are the. I didn't see the but they you were there when we got it. I love her with me. I love her. But I never again. We need one more person for my son. We need one more for my son. For what? But he's so much stuff together. Guess what I'm just like. Good one. Wait, we were all okay, no, but they would go together. They were like yeah. I don't know that's why next time you're coming. I don't care if you have a quiz. This is one time in class.
I think yes.
Okay, you were a blocker. You were our blocker.
Well, please take it.
No, I think I would love people to focus. Why is it that you were like oil and water? Oil and water? No, oil and water. Are you heard? You're like oil and fire.
Okay, so let's examine this result. What did we get? We have found out that if we provide feedback of this exact form, where P matrix is given by this equation, we will minimize our quadratic cost in continuous case for infinite time horizon. These are strong assumptions. Hmm?
Is there always a solution to this? Even like numerically, is there always a solution?
Yes, there are even multiple, but we're interested only in the one that gives positive time.
Okay.
Yeah, so as in many quadratic equations, you can get a nonsensical solution that is backward in time. So yes, under the circumstances we have talked about previously, these matrices being symmetrical and positive definite in a necessary sense, it could be indeed solved. Well, if the system is controllable, but that's a different thing. So we actually are going to break both these assumptions in the simulation, and there could be problems linked to that. So if the time step is very big, the real behavior of the system will heavily deviate from the theory. And if the time horizon, the real time horizon we're interested in is small, this will not make sense again. But if we keep that in mind, it's okay. So it's just a slightly different problem. But we can apply the same intuition, and we can actually apply this result with just a solid understanding that it has some limitations. And there are other methods for exactly minimizing the cost in discrete scenario, and I hope we'll discuss that tomorrow. There will be a horribly big matrix there, I promise. But I mean, it's awesome in a sense. I was excited when I found out this method, but that's for tomorrow. So now let's take a look at this specific example of this thing. Let's again consider our precious system of a dynamic block, one-dimensional. Let's see how does this equation look like. So we're going to simplify where possible and let our it's not working. Is it? Do I have to shake? Okay, do you see the writing? Yeah. Okay. So this will be the simplest case possible. Identity matrix, the weight matrix, the cost matrix, the cost matrix actually. Our matrix is supposed to be an identity matrix of dimensionality 1, rectangular, square matrix. And what do we need here except for that? So we know A, right? A matrix is pretty simple. This one. B is the matrix that we are going to find. A we know, Q is there, B matrix. Okay, let's assume the mass of this block be equal to 1 because we're lazy. And this control matrix is going to have a form of 0, 1. So let's use this half of the whiteboard to write down this equation. A transpose is 0, 0, 1, 0. P. How do we define P? Well, the good news is that P is symmetric. So I'm going to represent it explicitly in the form of P1, P2, P2, P3. Then an identity matrix. And then this. our inverse will be just 1. And then B transpose B. And it is equal to 0, but 0 matrix, so element-wise. This is the algebraic recurrent equation. So let's simplify. Let's multiply all these things. Please do it on your own. Let's spend some time working on this equation. Then you'll appreciate that NumPy will do it for you, and SciPy. What we can actually do here is we can just multiply these matrices and assemble everything in the form of first 2x2 matrix being equal to the second 2x2 matrix of zeros, which will give us 4 equations, and they can be solved together as a system. probably will have luck, but maybe not. Let's see. How's it going? In the process, yeah.
Is the order matter in a second?
The second where?
Yeah, if I do 0, 1, 0, hash 1, like it's a PA and A.
Well, in general case, yes, because this one is non-symmetric. But I'm not sure that it will be easier to check it because I don't know. So I've done that, but not exactly precise result. Anyone needs help? assign two zeros element wise. Yes, we'll get a system basically.
You have to find one in Oh, these two questions are the same. Okay, we have three equations because these two are the same. We already have it.
So who is close to this solution? The right answer. Did you get any? So, please tell me. Zero. I'm not sure. So zero. Yeah, so intuitively we have to provide some kind of feedback to stimulate the system, so probably not zero. Any other options? So who is doing what exactly? You're in the process of transforming the system or solving the individual.
Is one B2 minus one?
Hmm?
Is one B? Never mind, never mind.
Yeah, it's very good. 1 plus B2 to the whole square is
We got 1 minus 6 minus 2.
1 minus 6.
Why did it never die from this? We subtracted this. Why did we subtract? No, it is subtracted.
Oh, so that, okay. My bad.
It's with the square. So why exactly?
We always take one.
Probably there's something. Well, the technical terms, one and minus one, but one of them is one of them but you're getting closer. Let's find the exact value now.
And then only two possibilities is that it is approximately one minus one.
Where's P3?
B3 is square root of 3.
P3 square root of 3. Yeah, so it is also square root of 1.
Square root of 1.
Yeah.
If you take plus minus 1 for P1,
Because if P2
then
is
it
square
is
root of 1.
negative 1 instead of positive.
How
But
do you
then
know?
would it be imaginary?
Nothing to be imagined.
No, if you put P2 is a negative 1.
Yeah.
Why
You
is
get
it
negative 2 plus 1.
Why is
It's just
P3
negative
equal
1.
to negative 1?
Like P2 is negative 1. If you put P2 is
P2
negative
is what? Not plus minus 1.
yeah, plus minus 1. If you put minus 1, you get minus. My last equation is 2P2 plus 1 minus 2.
Negative 2 plus 1 is negative 1 times 0.
So it's
Negative 1 and then positive P3 would be.
so that P2 has to be positive 1. Because we have
Sorry,
no
not my
problem.
bad.
P2 is 1.
This means
P2 is 1. P3 is plus or minus
So
2.
this was coming from P2.
P2 can I write only the positive absolute.
So
And this
P1.
can only be positive.
Oh, is it this?
P3
legally, like,
No, honestly,
like this.
no.
Okay, basically. I will look at it.
The same way you're trying to do. Have you done matrix calculations?
Yeah.
Just look it up. That's what we did.
Yeah, and
just
on a given set.
You need a differential set.
Yeah, so then
In differential,
one minus b squared.
we got.
One minus b squared. B minus b2
Yeah.
so that's 1 minus b squared. So b1 is square root of plus or minus square.
That was my.
What did you
It
get?
could be mine. Oh, just plus.
Well, figure it out. You can see why.
Am I missing out?
Wait, well, why can't it be negative?
No, why can't it be negative?
B2 has to be 1. Yeah, so B3 doesn't have to be 1, right? B2 is definitely 1.
One of them is an imaginary number,
Yeah.
and the path one is an imaginary number.
We can't take it.
If B1 is negative,
Yeah.
if B2 is negative one, B2 is imaginary
So we can't take
has
that.
to be 1.
Yeah.
Which means that this P3 has to be
Actually, it's plus or minus 2.
It's actually like just like.
Why not plus or minus? There is no mathematically considered plus or minus. Is
Like, not
is
sure.
B3
No, he's right. It can be plus or minus root
Which one is square root of 3?
3. P2 is positive 1.
Ah, yes, yes, you're right, correct.
Here.
Wait, B2 has to be 1.
Yes.
B3, if it's root 3, then B1 is minus 3.
No, really, the one
Oh, no, it's right.
Wait,
So B is only all positive. So B1, B2.
I have 3 questions.
But then
From them we get the function.
Yes. So 0 B2 is equal to plus or minus.
And minus
Plus or minus 1. Minus 1 we can't, definitely can't use plus or B2 is equal. Then B2 plus 1
We defined it. Yes.
it's plus plus then minus.
That's the A from there, and that's the B from there.
This is
We have
right.
0, 1
Oh, so we're not taking
But
negatives
for
at all.
the sake of this problem, we're taking it.
B2 is B3 is right?
And there's a Q and R
And we're not taking negatives.
Yes, and we'll discuss why. Okay, so who needs some more time to solve? Or we can proceed, there are multiple correct answers, so we can proceed. What do you think? Okay, let's proceed. And I'm going to use the precious fresh green marker. So could you please tell me the explicit form for the left-hand side of the equation? What do we get here? Could you help me? What are they?
So, yeah.
1 minus
1 minus
B2
yeah,
square.
1 minus B2 square.
B1 minus B2 times B3.
Yeah. And then
The same for the left
Same.
corner.
Mm-hmm.
And then
2B2 plus 1 minus.
B3 whole square.
Minus B3 square.
Yeah.
Mm-hmm. Yeah. So here we get 3 independent equations. This thing is equal to 0, this thing is equal to 0, and this thing is equal to 0. So basically we have 4 of them, but those 2 are equivalent. So we have a couple of options for B2. And Well, if you plug this into the second equation, get that P1 is equal to plus minus P3. We can consider the first case. Okay, let's just do it properly. 3, P2 is being equal to 1. What does this give us? Then P1 is equal to P3. So, yeah. Then the third equation turns into just 2 plus 1 minus P3 squared equals 0. So P3 is equal to plus minus square root of 3. And there are again two options. So in total, we're going to get 4 different options. And then let's, in order to choose a proper one, let's get back here and recall what are we actually supposed to get out of this. Let's plug P over here. So let's multiply. Let's get the explicit form for the feedback in terms of the magic speed. There's some kind of soul to the chalkboards, in the sense that you can erase from them in finite time. There's always a feel of satisfaction when you're, after the lecture, covered in the chalk. You're dusty. It gives a sense that something happened. The good news, I can still read what was here. Okay, so U is equal to minus R inverse, right?
Yeah.
R inverse, but that's just 1, because we have assumed these matrices to have very simple form. B transpose is 0, 1, I believe. And P will be, well, it has the form of P1, P2, P2, P3 times the X vector, which is X, P and P position. Okay, so X and X dot, if this will not confuse. And let's multiply that. And as soon as we get the exact form of this, it will be pretty clear which exact option we have to take out of that multiplicity of solutions. So first, let's multiply these ones because it's similar. It will raise certain things. So what we'll get is minus P2, P3, right? Times X and X dot. And it gives us minus P2 X minus P3 X dot, which is indeed the optimal controller for this cost. In terms of the, expressed in terms of the solution of the algebraic Riccati equation. So we know in advance that this feedback should be negative both in terms of the position and velocity. It has to eventually stop the system and it has to drag it to the origin. So this coefficient should be positive in this coefficient should be positive as well. And from all these four options, we actually have to choose only the one with the positive P2 and P3. So there will be a second option with P2 being equal to -1, but that will result in the destabilizing controller that will actually stabilize the system and backwards in time. We're not interested in that, so we pick only this option, and from these two options we pick only the positive one. And in the end of the day, the optimal controller for the costs set in this way, in continuous case for infinite horizon, will be precisely minus x minus square root of 3 x dot. And the cost of the whole trajectory up to infinity will be equal to x naught dot well, this thing, just the p matrix. So you can instantly calculate the cost, and you know the optimal feedback. The coolest thing about this is that it's optimal. It's the same for all the moments in time. You don't have to perform any additional calculations. You just do it once, and then the only thing you need to do in order to calculate the control is to do a couple of very simple operations, not even with matrices. So just multiplication of the elements of the state vector by certain constants, and you have the proper feedback that will stimulate the system. This is the coolest thing about the LQR. It gives full state feedback, and you don't have to perform any kind of additional calculations. So it could be run on a wristwatch, headphones, anything. Very small devices. So what I propose to do next is to complete the notebook in Collab at home. Here in the notebook you can, well, first there's the derivation for this case. And you can try out and compare the cost that will just any other controller give you with the cost that will be obtained with this optimal controller. I think that's it. If you are brave enough, you can try to proceed in the notebook up to solving algebraic Riccati equations with software tools. There's nothing scary. You just have to read the code, and that's it. That's fine. So we're going to talk about it tomorrow, or we can talk about multi-predictive control. We'll choose tomorrow, or we can talk about both. And unfortunately, tomorrow is the last day. At first, it's the short day, and second, it's the last day when I will be teaching control. After that, you're going to have practice with robots. And regarding the control, probably it will continue in September, but probably, I don't know. So I'm not sure if it will be control or computer vision, but anyways. So thank you for coming. See you tomorrow.
Quick question. So now we found KP and KD. What about PI? If you were doing a PID
It will be not a full state feedback, so it's not solvable by in this way.
Okay, so because you're taking the integral, we need to know the previous states.
Yes. It's not a state feedback, it's like a story feedback.
Where would PID be more useful? Where would your PID be more useful than PD? Like, where would the PID controller be used for?
If we have some kind of static or static relation or some kind of flowing state direction. So imagine the following. Imagine that you're trying to stabilize a pendulum in that right position. And there is a wind blowing from the left. So at a certain angle with no velocity, the torque by the proportional part of the controller will be precisely compensated by the wind. And this pendulum will be stuck at this position for an infinite amount of time. Because the same force is being produced and the same wind is being produced.
We don't know exactly how much, like, so because this is basically what we call like noise. Noise that keeps it in a particular state.
Well, the integral part will not account for the noise.
Say for example, like, we knew the coefficient of we knew all of that, and like we just subtracted the force of the wind from the top.
That's a nice way of doing so. You can relate that to some kind of compensation if you know the parameters. If you don't know the parameters, we can relate them with the help of so-called control Lyapunov functions. But that's a different. So we can define a certain function and try to minimize it. And the only point where this function will be equal to 0 is the point where the system is stabilized and we know the proper parameters of the system. But it's just another thing I will show at some point.
Someday.
I think so. Do you know where her office is? I think so. Guys, do you know where is the office of Dr. Julia?
I'm working on it.
Yes. Please stop it.